Hello, everyone. We are the senior project team, and we are currently working on a Planarizer. Now, before I get into what a Planarizer is, I will introduce you to the scope of our project. The members of the Cal Poly legged robots team are currently working on a quadruped robot. They have been working on a 2 degrees of freedom single robot leg through a senior project team, and have been researching the dynamics of this leg through a summer research project, as well as a master's thesis of a student. What our task is to come up with a restraint mechanism for this leg that will allow it to move with the leg and constrain this leg within the sagittal plane, which is essentially a plane that divides through the center of the human body, cuts through it. And another need of this Planarizer is to collect the leg's positional data without adding any inertial or a significant amount of inertial or vibrational effects to the dynamics of this leg. You're muted, Eric.
For this project, the sponsors, the Cal Poly Legged Robots Club, were also our only customers. We met with the club leaders in bi-weekly meetings to discuss not only their basic needs, like collecting the position of the robotic leg, but more specific demands, such as making a catch mechanism and optimizing the time to read the actual collected data.
In terms of some of the other research we have done, we have looked at similar mechanisms or products that are aligning to our Planarizer model. One of them we looked at is Hoppy. It is a small boom base robot that was developed by the University of Illinois by the mechanical engineering students. It has a robot leg actuated by 2 motors attached to a shaft, which is the boom centrally. And it has a 2 degrees of freedom gimbal mechanism at the center base that allows for pitch, as well as yaw motion in the 360-degree circular plane. It also uses a counterweight to provide some gravitational compensation. The other product we looked at was Mabel and Thumper, which are also student-based robot boom-based projects, but they are much larger scale. And they have overhead restraint mechanisms as well, in terms of a cord attached to the leg, as well as a pole attached to the base in the center, which is attached to the ceiling. In terms of what types of restraint mechanisms we looked at, we read through some master's theses, and we read about a boom and base model, a linear Planarizer model, and an overhead crane model. The linear Planarizer model uses linear bearings on a vertical and horizontal rectangular shaft. They move along these shafts in the rectangular plane shown here, meaning that it is an excellent sagittal plane approximation. However, it is very difficult to maintain continuous motion, and continuous motion is important for the sake of a Planarizer, because the positional data of the robot must be kept with fine resolution, and many data points must be collected, and having that capability of continuous motion allows for this. You'll see a treadmill is used in figure 2 on the right hand side in conjunction to a linear Planarizer to provide as a source of continuous motion. The issue with a treadmill is it has a large footprint, meaning it is very large in size and is difficult to store and not easy to move around. It is also very expensive and not necessarily the most practical option. The boom base model incorporates aspects that Hoppy incorporated, which means it has a long boom as shown in figure 3, which allows for this good sagittal plane approximation. The continuous motion is possible with a boom base model because the robot leg is hopping in a circular path. It also can be collapsed and stored easily if it is designed to be folded along different lengths of the boom. The other restraint mechanism is the overhead gantry. It is a stable option because it is permanently installed to the ceiling with rails that go along the ceiling as well as linear bearings and a crane. However, it is very bulky and hard to maintain and is very permanent.
Some of the technical research we looked at also involved how we can collect data from the moving robotic leg. To do so, we plan to use angular optical encoders. Angular optical encoders allow us to collect accurate angular data, which then we can use to find the position of the robotic leg. We can use 2 angular encoders on our device to find both the vertical location and the location of the leg on the track.
Continue, we constructed a functional decomposition to illustrate the key functions we want our Planarizer to have. The most paramount one is to be able to collect positional data where we want to track the motion and the velocity of the robot leg. We also want to satisfy customer constraints and provide a friendly experience where we're able to make a portable design that also accommodates possible different leg sizes for future use. Also with this, we wanted to limit dynamic effects so as to limit vibrations if we were to go over natural frequencies to avoid resonance, and to also avoid foot slippage so that the leg can consistently hit the ground. This will also protect the leg from damage so that we can continue with repeated use of our Planarizer. Continuing with the process, we created a Pugh matrix for each person. With this Pugh matrix is on a plus, minus, or 0 scale, where the 0 S just means the same. And it all is compared against a datum, where it would just all be S's and just a datum of 0. With this, we each created our ideation models, and you can see pictures of 5 of them at the top. And then we would weigh this against different customer specifications and designer constraints. For example, how affordable we think this may be, or how portable, easy to move it may be. We would rate each of these on a plus, minus, or 0, tally them up, and then rank it, with the highest ranking being our best ideation model. So for some examples of design considerations, these first 2 were mine. The first one, I created 2 L bars put on the side of the boom that are supposed to act like training wheels so that the Planarizer doesn't tip in the yaw direction, so that it can stay sagittally straight. And then for design 2, I created 3 hinges, 2 on the boom and then 1 at the base, to illustrate some possible portable designs that we could create with our Planarizer.
The next 2 designs we considered, designs 3 and 4, are shown. Design 3 is a simple boom and base model. However, what makes it unique is there is a cord attached from the end of the boom to the ceiling or any other placement that is above the boom. The special thing about this cord is that it is elastic, so it offers an excellent source of gravity compensation in terms of limiting the effect of the weight of the boom that is felt by the leg each time that it hops in its path. Design 4 is a design that has a counterweight at the end of the boom and the leg at the other end of the boom, and it is supported by the base in the center. The counterweight also acts as a form of gravity compensation, limiting the amount of weight that is felt by the leg.
Two other design choices that we considered were the treadmill and the freely rotating cylinder. In both of these designs, the robot would end up jumping up and down in place and under its own power. Either it would maintain its position on either the moving treadmill or it would push the freely rotating cylinder. We would then be able to track the speed of the robotic leg using either the treadmill speed or the cylinder's angular speed.
The last two of the top 8 design ideations that we had are design 7 and 8, where design 7 is pretty similar to design 3. It's a boom and base model, but it just doesn't have a catch or a weight compensation implemented into it. Design 8 is a 2-bar linkage that takes a pretty similar approach to the linear bearing restraint mechanism discussed earlier on, but instead this would involve 2 slotted links that are connected at 2 pin joints to the ground, and this would allow it to collect data within the sagittal plane and perfectly restrained to the sagittal plane. The only problem it would have with just the 2-bar links would be it wouldn't provide continuous motion, and so a treadmill is added on to make sure that it would be able to come up to steady state gait.
Continuing with our process of controlled convergence, we created a decision matrix where each 4 of us, we put up our 2 best ideation models in preparation for our controlled convergence and what form factor we want to proceed with. With this, we have assigned weights that we found from our QFD. And like, for example, some of them may be cost, like how expensive we think one may be relative to another, or what mass increase it may allow. And when we scored each of these criterion on a scale of 1 to 5, we multiplied the weights together and summed the total to find the overall score. And once we deliberated on this process and found the ranking for each one, we found designs 3 and 7 to be our best designs with the boom base model with a possible catch mechanism for our final concept prototype.
As mentioned earlier, designs 3 and 7 were seen as the most feasible options. Our concept CAD was focused on design 7 specifically. You will see at the top, there's a pivot connector U-shaped bracket, which has a hole drilled into it with a pin attached through it and through the boom as well. This allows for the pitch movement of the boom as the robot is moving up and down. The yaw 360-degree movement is allowed by bearings that are placed on the base shaft. And these 2 bearings rotate around the shaft as the robot is moving in its circular path. And bearings are attached to square plates, which are attached to rectangular plates, which are attached to this pivot connector, allowing the whole assembly to rotate with the leg in the circular path. You will see we prototyped based on this CAD assembly, with the PVC pipe being the boom and another PVC pipe being the base shaft. And you will see the yaw connection assembly on the right picture with a boom, a base cap, fence post, metal hanger used as a pivot connector, and a wooden dowel placed through it as well as through the PVC pipe to allow for the pitch movement. And I will now show you a demonstration video of pitch and yaw in motion with the prototype.
Moving forward, we're going to be looking at the potential issues and risks with the design, just everything we're going to want to make sure that we can account for and help prevent. And so some of the ones that we've considered so far are the battery possibly overheating. This would be the battery for the DAC. Right now, we're considering using a 9-volt battery, and to avoid any fire hazards, you want to make sure that the two leads can't connect and short the battery and cause some kind of fire. So we're probably going to be providing some kind of battery cover. For the boom, we want to make sure that it won't vibrate at its resonant frequency at any point. So we're going to try and design the natural frequency of the boom so that it's significantly above whatever frequency we believe the robot leg might drive the boom at. For data resolution, basically we're just concerned with making sure that the data is going to be usable, that whatever we collect is good data, and so we will likely be just selecting encoders that can read the pitch and yaw of the boom with a high enough resolution to accommodate this. System noise, we want to make sure that the data that we have, again, is readable and usable. So we're going to try and come up with a list of whatever we think could result in some system noise. One in particular that we thought of is just boom vibration. In particular, we're going to be looking at trying to minimize the amplitude of the boom vibration, so probably just tip affection, and hopefully that'll reduce the greatest source of system noise. For the leg, we want to prevent its damage in the case that it falls over, and so we're looking into putting in a catch mechanism that will basically just make it so the leg can't fall in a precarious position that would create a lot of damage to the leg. And then finally, we are looking at minimizing inertial effects. So one big part of that is moment of inertia, as we're going to have this robot leg rotate about a fixed point. And so we are starting to try and look into analyzing the system, analyzing the dynamics of implementing a restraint system to make sure that the apparent mass moment of inertia or the apparent mass that we add by attaching the restraint system is minimized. We just want to make sure it's not like too big to the point where it will have an actual effect on the leg, as we're trying to test actual leg motion without restraint, but we have to simulate with the restraint.
All right. Looking forward for next week, last week of 428, we have to make our FMEA, also known as the failure modes and effects analysis, where we will focus on the most likely characteristics out of Planarizer to fail. Because it is unlikely to focus on every single failure and try to stop it, we are focusing on failure management, where we look at the most likely spots and then focus on reducing the chance of failure yielding in that direction. Looking forward in 429, we have the IDR and CDR, the interim and critical design reviews, where these are multidiscipline technical reviews just to prove that we can go through to the next stage in manufacturing. So in this report, we will prove that we have met the requirements within costs, scheduling, and risks, and that is all accounted for. So we will be looking at that next quarter.
Thank you so much for watching our presentation. If you have any questions or comments, please feel free to reach out to us.